just the definitions here. A Lewis base, if you remember, this is something we learned back in chapter 16.
Yes.
A Lewis base is something that donates a lone pair of electrons. Then the Lewis acid is the thing that's accepting that lone pair of electrons. So just a case where you have a Lewis base would be something like ammonia, because it has that lone pair of electrons that it's going to donate to something like boron trifluoride, which is acting as a Lewis acid. And so that lone pair of electrons gets donated to that boron, and it forms that bond there between the nitrogen and the boron. Okay, and the thing about it is normally if you think about a chemical bond, it's where each atom provides one electron in the bond. But in the case of this bond right here, both of the electrons in this bond came from the same atom, from the nitrogen atom. So that's what makes it unique. Okay? Now, there's a little bit more to it. And so when you have complex ions, you have a couple areas that you want to know about. The first one we call the inner coordination sphere. And so that would be the ligands that are actually bound directly to a metal through those coordinate bonds. Okay. But then you also have this thing we're going to refer to as the outer sphere. And so that's when you have essentially your counter ions. So they're not bound to the metal, but they are present. They're mandatory. They have to be there because anytime you have a positive charge, you have to have a negative charge to balance it out. So that's what those outer sphere ions do. They neutralize that charge in the complex ion. So in your handout, you have this picture, and it just illustrates a lot of the things we just defined. So for example, these little gray sticks here, those are your coordinate bonds. Okay, those are your coordinate bonds. Now, incidentally, you notice over here we have these dashed lines because those aren't really you could argue whether or not those are real bonds. We talked about this back in Chem 1. That's just those dipole, the ion dipole intermolecular forces at work. But in this case, what you have here are, first of all, these would be like outer sphere chlorides because they're just there to neutralize the positive charge on this chromium metal, or pardon me, cobalt metal. So this is cobalt +3, and so I need 3 negative charges kind of hanging around to neutralize that +3 charge. So those are all what we would call outer sphere chlorides. But then you could have a situation where one of these chlorides could replace one of these ammonia molecules, and that's shown right here. So then it would become an inner sphere chloride, okay? Because now it's not just hanging around to neutralize charge. Now it's actually formed a coordinate bond with the metal ion. Okay, so that's the distinction. And you can see right here that it makes a difference in terms of the properties of the substance. So this is an orange colored complex ion. This is a purple colored complex ion. So it has different properties based on whether the ion is hanging around in the outer sphere or whether it's actually bound in the inner sphere. Okay? All right, so something we learned back in Chem 1, there's quite a bit of Chem 1 review in this lesson today, is we learned this thing called VSEPR theory, and it was determined the geometry of the compound, whether it was linear or the tetrahedral or the octahedral or the square planar. So all of those were determined by the electron pairs around the central atom. Well, when that central atom is a metal, we also can assign something called a coordination number. So coordination number, by definition, is something that identifies the number of electron pairs surrounding a metal ion in a complex. Okay, and so, for example, if it's linear, we would have a coordination number of 2 because it's got these 2 electron pairs where it's bound, or another way to think about it is this metal in the middle is connected to 2 atoms, okay, as ligands. Okay, so there's a ligand, forms a bond, another ligand that forms a bond. So because those ligands occupy 2 positions, it has a coordination number of 2. Well, if the ligands occupy 4 positions, and that can happen with a tetrahedral geometry or a square planar geometry, the coordination number is 4. So it's as simple as just counting the number of positions that are occupied by ligands in the complex. All right, and so this one where we have a metal in the middle with 6 water molecules surrounding it, if we consider those to be coordinate bonds, then there would be a coordination number of 6. All right, so that's something I want you to be able to do. If you're looking at the structure of a complex ion, can you identify the coordination number of the metal? Okay, so it just identifies the number of electron pairs surrounding a metal ion in a complex. Okay, so these ligands, let's talk a little bit more about these ligands. We've already said that they're Lewis bases that form a coordinate bond with a metal ion. Well, they can do that in different ways according to their characteristics. And so one way is through this thing that we call a monodentate ligand. And so that's where it just forms a single coordinate bond. Okay, so that's a species that forms a single coordinate bond to the metal ion in a complex. So some examples of that would be like ammonia or chloride. They can just form one coordinate bond. So these ligands, these two ligands, can only form one coordinate bond with a metal. But there are many examples where you could have multiple bonds formed with the metal. We call those polydentate ligands. So those are species that can form more than one coordinate bonds per molecule. And then another name for that is this process we call chelation. That's how you pronounce that, chelation. Okay, and the thing that does that is something we call a chelating agent, but it's just a ligand that is polydentate. So it's the interaction of a metal ion with a ligand having multiple donor atoms. So a ligand that can kind of really wrap itself around the metal is what you're talking about here with chelation. Okay, and that name comes from actually the Greek word for like crab claw. Okay, because you can imagine if a crab locks onto something, it's very difficult to remove, right? Well, these ligands that do this thing, do undergo chelation, these chelating agents, they really stick to that metal. The formation constant, the K sub F, if you remember that from back in chapter 16, that formation constant is very large. It's very product favored. Okay, so here's an example of a bidentate ligand, a polydentate ligand that we call ethylene diamine. So it's bidentate because it can make two coordinate bonds. Each of these nitrogens can form a coordinate bond with a metal. So the abbreviation that's often used for ethylene diamine is just EN. And so here is an example of ethylene diamine bonding to a ligand. So these are three different ethylene diamine ligands, okay? And they each can form two coordinate bonds, okay? And so the overall coordination number of this complex ion would be 6 because this metal in the middle has connected to, the ligands in 6 different positions. Okay, so this would have a coordination number of 6 because it forms 6 coordinate bonds. Okay, it's 3 ligands, right? But its coordination number is 6. Okay, and here's one that can actually form 6 coordinate bonds, and it's called EDTA, or ethylene diamine tetraacetic acid. And it's often used as a sequestering agent. So anytime that we want to remove a metal from some sort of solution or something like that, if you want to sequester it out of a mixture, then it's common to use this particular ligand called EDTA. And so this is just a picture of cobalt plus 3 EDTA. And so I won't go through, but it's kind of color coded. All the blues represent nitrogens and the reds represent oxygen. So you can kind of see. But the big thing to look at here is that there's 6 coordinate bonds here. 6 coordinate bonds formed with the cobalt, and all of them come from the same ligand. So this is kind of like the example of a chelating agent. EDTA is a very common chelating agent. It just really wraps itself around that metal ion, and like I said, it's a very product favored reaction. So once that happens, it's challenging to remove the metal ion from this bonding arrangement. Okay, and so for example, you'll see EDTA a lot of times as an ingredient in food if you look at the list of ingredients. And the reason why is because metal ions, like not necessarily cobalt, but a lot of times these metal ions, they're the culprit in spoilage of food. Because if they get oxidized or if they get reduced, usually it's the oxidized, but that redox reaction that occurs is what begins the spoilage process. But if I can wrap that metal ion up with EDTA, then it's not as likely to undergo that redox reaction, okay? Because it's not going to be in contact with anything that can react with it. That can actually transfer electrons to or from it. So that's why it's pretty successful as an anti-spoilage agent, and so it's used a lot of times as an ingredient in food, and it's harmless. Okay, and we'll talk about another application for EDTA in just a second. Okay, but here's another one. So EDTA is one chelating agent, but here's another important one called porphyrins. So they are tetradentate. They can't form 6 bonds like EDTA. They don't form 2 bonds like ethylene diamine. They form 4 coordinate bonds, all in the same plane. And so you can see if you take a porphyrin group and you expose it to a metal ion, usually what happens is the metal inserts itself into the middle and it forms this square planar kind of arrangement, right? And so you have this metal porphyrin complex. And so we see these in biological systems quite a bit, and we'll show you an example of that. Okay, so now another topic that we want you to know about these complex ions is a little bit, pardon me, about what we call stereoisomers. And so let's say that we have this platinum complex ion where we have 2 ammonia ligands and 2 chloride ligands. So there's a couple ways that we can arrange that. We can arrange it in what we call the cis geometry, or the cis stereoisomer, or the trans stereoisomer. Okay, and what is a stereoisomer? Well, it's 2 or more compounds differing only in the spatial arrangement of their atoms or ligands. You can think of it as the way the ligands are arranged as well. And so in the case where you have the cis arrangement, it's where they're both on the same side. So it's the same sound, right? Cis, same side. That's the easy way to remember it. So both of the ligands occupy the same side. And the trans is just the opposite. Okay, so in the case of the trans arrangement, the ligands are on opposite sides of the complex. Okay, and so as you'll see in just a second, that's important. It's important for the chemistry that can occur. Okay, so the trans is the opposite sides. Okay, so why do I want you to know that? Well, like I said, it does affect the properties. So if you have the cis platinum, the chlorides on the same side, the cis arrangement, that's something that we call cisplatin. And this is actually an anti-cancer drug. So what happens is these 2 chlorides can come off, and that cisplatin can connect to the DNA, and it more readily connects to the DNA of cancer cells. And so what happens is that leads to essentially you start cross-linking the strands of DNA in those cancer cells, so you get DNA damage, and so that's going to inhibit the cell proliferation. So it's one way to combat cancer. So because if the cancer cells can't replicate their DNA, they can't proliferate, and therefore they die eventually without undergoing mitosis. So now, of course, this happens to healthy cells too, but the idea is that it happens to the cancer cells faster than it happens to healthy cells, and so that's why it's a pretty successful anti-cancer treatment. But it's important because only the cis arrangement works. The trans arrangement does not work. It does not kill cancer cells. So that's kind of an interesting thing about this stereoisomers that shows up with these complex ions. Sometimes. Okay, just some more complex ions to illustrate why this might be something you want to think about. They're often in enzymes, or we call those metalloenzymes. Here's an example of one: carbonic anhydrase. Right. So we have zinc is a metal ion in the middle, and it's got all these ligands forming these coordinate bonds with it. These are histidine residues on a protein. So this green strip you see here represents protein. Okay, and some of the amino acids in that protein are histidines, and so a few of them come together with just the right geometry that it can incorporate this zinc 2+ ion and also leave a spot for a water molecule to bond to that zinc ion. And so what happens is that zinc catalyzes that water molecule to break up into its hydroxide ion. And then, we know that in our cells, there's also carbon dioxide present. It's a waste products of cell respiration. Okay, and so that hydroxide ion can react with that carbon dioxide to create the overall chemistry is you have a water molecule combining with carbon dioxide to form a bicarbonate ion and H+. And so that is a very important reaction that's catalyzed by this enzyme, this coordination complex, right? Because that's our pH buffer in our body. We know that all the biochemistry in our body is very pH specific. So we want to maintain a steady pH. And so this is the reaction it's the major reaction that's responsible for maintaining the pH in biological systems, in mammals at least. And what's responsible for that in large part is this coordination complex. So we got the zinc, this metal ion in the middle, and we have these ligands forming these coordinate bonds. And because of that, we have this buffer in our body that sort of, enables all of these other very, very important biochemical reactions to occur. Okay, so just trying to highlight, the coordination complex part of this enzyme. Okay, so I mentioned porphyrins earlier and how they were important in biological systems. So here's an example of that. So if you put iron into the middle of that porphyrin, what you have is a heme group. Okay, and heme groups show up all over the place in living systems, but most importantly, when you have iron in the middle, okay, that's hemoglobin. Oops. Okay. And so all those places where iron is in a porphyrin group, those are in molecules known as hemoglobin, and there are four of those porphyrin groups in every hemoglobin molecule. And of course, that's responsible for transporting iron throughout the body. So it's when the iron gets absorbed into the bloodstream in our lungs, it finds these hemoglobin molecules, it connects to the iron, and then that oxygen gets transported throughout the body to the cells wherever it's needed to undergo cell respiration to make ATP and all that other good stuff that goes on. So again, fundamentally, this is a coordination complex. You have the metal, and it's connecting to all these ligands, right? So, just wanted to give you some biological examples of these coordination complexes. All right, a couple more things. So, the chelating agents, another use of that, I already talked about how EDTA is often used to keep food from spoiling. But also it can be used in a treatment to remove toxic metals from the body. It's FDA approved for a few situations, like lead poisoning. If someone is suffering pretty severely from lead poisoning, you can dose them with EDTA, and what happens is the EDTA will find that lead and they'll bind with it, right? And so it forms this complex that's no longer toxic because that formation constant, the equilibrium constant that governs the formation of this product, is a very large number. Okay, so it's very product favored, and so that's why it works. It works to get rid of heavy metals, toxic metals from the body. Okay, a lot of times these chelating agents, like citrate, you've heard of citric acid. Well, citrate can be used as a chelating agent. I mean, all these oxygens, you see these three oxygens, they can sort of bind in three different places around a metal, and so any sort of diagnostic or therapeutic agent is often delivered into tissues with the citrate ligand. Okay, so that's one possibility. Here's another one that kind of combines, the other topic that we went over in this chem potpourri unit, and that is radioisotopes, radionuclides, and nuclear reactions. So if I have like these two rhenium isotopes, rhenium-186 or rhenium-188, and I select the ligand, the chelating agent carefully, then I can use that in a couple ways. So you notice that this, I don't know if you do recognize this, but this is like a peptide chain. Okay, so it's got some amino acids in it, and on the end here we've got this carboxylic acid that can also incorporate into a peptide chain, and you'll learn more about that in biology and biochemistry if you take biochem. But that's very important because what we can do is a couple things. This is certainly going to be a toxic metal if it were free in biological systems. But when I sequester it into this, or when I, kind of wrap it up in this ligand, it's not toxic, all right? Because, that formation constant is so large, it's not going to easily get rid of that ligand, right, to make it available for absorption into the cell as a toxic metal ion, okay? But the other thing is that if this is radioactive and I can make this specific to certain cells, then I can do two things with it. First of all, I can maybe kill that cell, like if it's a cancer cell, with the beta. If it's a beta emitter, that beta minus particle could, that radioactive particle could kill that cancer cell. But then also I can know where it's at because it's going to emit a gamma ray. Remember, most nuclear reactions also emit gamma rays, and you can detect those, and you can detect those outside the body because the body isn't very good at shielding it. These gamma rays don't interact with the material that they travel through very likely. It's not very likely that they're going to interact with the material that they travel through because they're not charged and they have no mass. So they have a large penetrating range. And so if I use a beta emitter like rhenium-186 or rhenium-188, and I can get it connected to a cancer cell, first of all, I have a chance of killing that cancer cell because it's going to spit out a beta minus particle, which is going to damage that cancer cell. But also I can detect that it's there by, I can have special instruments that detect those gamma rays that are also emitted at the same time this beta minus particle is emitted. So the beta minus particle could kill the tumor, but then also I can know that it's in the right place because I can detect the gamma ray that's coming from the beta emitter as well. And so this is actually something that is used in cancer therapy. I apologize for this graphic isn't very, it's not a very sharp image, but it was the best one I could find. I liked it. So again, there's a name for this. It's called peptide receptor radionuclide therapy. And so if you have a radioisotope, like one of those rhenium isotopes I just had on the previous slide, it gets bound up in this chelating agent. So the ligands form these coordinate bonds with this radioisotope. But also that something that's unique about this chelating agent is that it can connect to a peptide, right? And so a lot of cancer cells, they like to bind on their surface peptides, these peptides. And so that what is nice about that is that they are, these radioisotopes, these radionuclides are going to selectively be absorbed into the cancer cells because these cancer cells like to connect to these peptide chains. And so it introduces all these radionuclides into the cancer cell. They do their thing. They emit the beta minus particle, which is going to damage the cell, hopefully kill the cell. But they're also going to emit those gamma rays, which we can detect to kind of see it working with these imaging devices that they have in the hospitals. Okay.